So hello, yeah, good morning, everybody in China, and good evening in the USA. And welcome all of you join this internet open seminar in Frontier of Nuclear Physics. This open seminar was organized by Fudan University, Department of Nuclear Science and Technology, as well as the Institute of the Modern Physics. And today is series 24th in this open seminar. And this open seminar was also co-organized by the Journal of the Nuclear Science and Techniques and Nuclear Technology. And this seminar was also simultaneously distributed by the co-share science platform. And today we are very happy to invite Professor Paul Danielewicz to give a seminar Deblurring for nuclear three-dimension characteristic of heavy ion collision. And before the talk, I would like to introduce Professor Paul Danielewicz briefly. Paul Danielewicz is a famous nuclear physicist working at the Facility for Rare Isotope Beams and the Department of Physics and Astronomy of Michigan State University. He is also a fellow of the American Physical Society. He is an expert for nuclear transport theory and has a lot of genuinely significant contribution to the nuclear reaction dynamics and heavy ion physics. His major works include transport theory for the reactions, collective flow, influence of the bulk nuclear properties, and non-equilibrium Gerling's function theory. For example, he published a very famous paper on science for the nuclear equation of the state for nuclear matter. He also presented a very famous method for the reaction plane determination in heavy ion collision, I think, which was very extensively adopted in heavy ion collision community. So today he will give us a talk for Deblurring for nuclear. And so let's invite Professor Paul to give us this seminar. So Paul.
So
yeah, it's good.
It's good. Yeah. Mm-hmm. So my talk today will actually pertain to the reaction plane, but also to other problems in nuclear physics. And I will advocate so-called Deblurring methods transplanted from optics that may be beneficial when used in the context of nuclear and particle physics. And in particular, they can be used to see the full three-dimensional characteristics of heavy ion collisions, circumventing any problems with determination of the reaction plane. So actually, I'll push away from the method of determination of the use of the reaction plane as till now. All right. So what's Deblurring? So Deblurring is commonly used in optics. It's actually used in many practical situations, some that you may be aware of and some not. So for example, you face the problem of a blurred photo when you take a photo of a moving car with the finite exposure time. You try to, for example, magnify the region of the photo where the registration number is. You will see a blurred image, and you cannot read what the registration number is. If you apply Deblurring to that photo, you get this image here shown in the center. And actually, it compares very well with the photo of the same plate taken for a parked car. So here I have an example from a photo taken actually in Beijing area. So it's a moving car. When car is quickly moving, you take a photo, you look at its details, you see sort of smudged, characteristic smudge in the direction of motion. Again, this is magnification here of the registration plate. And after, if you don't apply deblurring, this is what you have. If you apply deblurring, you begin to be able to read the number. And actually, you can read that this is a registration plate from the Beijing area, and it's a foreign-owned car. Okay, and you have the registration number. And of course, people get, you may say, oh, you know, it's not, you know, maybe the blurring is somewhat suspect. Well, people get tickets, and it's commonly used by police in determining what car exceeded the speed limits. The blurring is broadly used in microscopy. In fact, very often when you see photos for research papers, they are routinely deblurred. You don't, very often it's not even stated because it's obvious that they are deblurred. So if you take a photo through a microscope, optical microscope of some microscopic organism, this is what you normally would see. Usually these photos are taken over layers. All layers look like this. And then you apply deblurring, and you begin to see these are two cells, and there are various structures in these cells. And this is normally the blurred image is what gets published and it's used to draw scientific conclusions. The blurring has received a big push in astronomy. And this happened after the Hubble Space Telescope was sent to space with an optical flow. And all its early images were blurred. So there was, around that issue, there was a very strong push in astronomy to develop deblurring methods to get sharp images out of the blurred ones. Fortunately, the Hubble telescope was quickly repaired, so actually it ceased to be necessary to rely strongly on deblurring to get good images from that telescope. But the deblurring got, because of this, a lot of attention, and actually after that, a lot of development happened. And here, for example, you see an image of a lunar crater that's directly taken with a telescope, and that's what you get after deblurring. So how does deblurring work? So basically, in deblurring, you correct for the flows, understood flows of the apparatus. Very often, you actually figure out what those flows are during the deblurring process. So very often, for example, you don't know a priori in which direction the car moves and at what speed, but during the deblurring process, you actually iteratively determine that, getting a clean registration plate. So how do we work nuclear physics or particle physics and correct for distortions? So let's consider some measurement with a detector which has some detector efficiency epsilon. So the fraction epsilon of particles gets measured. We measure n, lowercase n number of particles, but the actual number that we would like to know is capital N. So we take measured number, divide by efficiency, and we get an estimate for the actual number of particles. So that's the normal procedure. Now, at times, we deal with a situation where a slow particle goes out of a thick target, and then it experiences energy loss. We estimate that energy loss, some delta E average, and we measure some detected energy particle at the detector E dt, and we correct it for the energy loss, and then we can estimate the energy at the production vertex. But how to go beyond that? So beyond that, we can state the problem probabilistically. We have, given the method or detector or any kind of framework we have, particles come out, they have some characteristics psi, but with certain probability distribution, we measure actually some properties zeta, and maybe we don't detect the particles at all, they miss them. And overall, the number of particles measured with some property zeta can be represented as a convolution over all possible values of psi distribution of particles with properties psi times that conditional probability p zeta at psi. If detector is introduces small measurement distortions, so for example, this energy loss is small, then this p is finite only when these two characteristics are close to each other. So we can say along the diagonal, when characteristic zeta is little different from psi. In optics, this kind of convolutions are used, and these n, capital N and lowercase n are photons. And this conditional probability is called a blurring or transfer function. And basically, the problem of the blurring is to figure out n, the real number of particles with certain properties psi, when we measure particles with typically a reduced number at properties zeta. So that's the deblurring problem. Now, there are various deblurring methods, and one that I will advocate is actually based on Bayesian considerations. So if you understand your detector or your method, you can construct this probability of measuring zeta when actually particles have properties psi. For example, in experiment, this is normally done with simulation software such as Gian4. In many cases, in sort of easy cases, the problem will have a linear form. So P will not depend on N. But in reality, very often you will have situations where P also will depend on the number of actual particles that got emitted. For example, the tracks merging. When you determine reaction plane, you determine the reaction plane from all particles in the event. This P will depend on N. So there are many situations where P will depend on N. I will argue that you can still apply the blurring when P depends on N, when the problem is nonlinear. So what about those Bayesian considerations? So let's consider just theoretically a complementary probability that when you measure this probability will be also a conditional one, probability that when the particle has been measured with property zeta, it actually had characteristic property psi. We don't know that probability, but principally it exists. If you knew this Q, you could actually easily invert the problem, and knowing this lower n, you could find capital N. That you would have our problem solved. But we don't know it. So we can write a Bayesian relation and write the probability that a particle has actual characteristic in some interval d psi, while it gets measured in the zeta, d zeta. We can write that probability as n number of particles with property psi times d psi times d zeta times p, probability that the particle got measured with zeta. In a complementary way, you can write it in terms of q multiplying a number of measured particles times d psi d zeta. That's a Bayesian relation, just basic Bayesian identity. Now, from that identity, you can actually integrate both sides over d zeta, drop d psi, and you can actually write what n of psi would be in terms of q. You have this relation. On the other hand, you can move this factor to the left, divide by the left, and you can write what q is in terms of n. So you can say, well, these are just consistency relations. I mean, as long as we don't know n and we don't know q, we cannot move forward. But in optics, actually, these two relations have been attempted to be used in such a way that you write them, and you begin to solve them iteratively. So you don't know what q is, but you can make a guess for n, put it in, p, you can calculate q. Then you take that q, you put in this relation, and you get n. Then you put n, you take your new n, you put it here, and you find new q. And you just carry on until stabilization. And if you combine those equations, you can actually develop practical procedures. So for one, when you carry actual measurements, you will not treat properties as continuous, but you will bin those properties in some manner. For example, this may be bins in energy, in angle, in momentum, some kind of characteristics. But also the characteristics may be discrete from the beginning. For example, you misidentify protons as deuterons, or the other way around, or pions, and you can write such relations. If you combine those equations, the set of equations that you begin to solve is the following: this is your guess for what the true properties, what the number of particles is with true properties. You calculate from this the likely outcome in iteration R. Then you put that n, this projected outcome, and you compare it to the actual outcome. You take the ratio, and then you convolute it with this conditional probability. From that, you get an amplification factor, which you apply to your previous guess for the real number of particles. When all these quantities are bins, these become vectors, and these become matrix multiplications. Very often, as a start, you may assume that whatever you measured is actually true. It's actually represents reality. Other starting guesses are you take n, which is uniform over property. There are different ways of progressing, and then you just iterate it. You can find the description of the algorithm with some shortcuts in Wikipedia. There are other methods for this Deblurring, which include Fourier transformations, but many Deblurring methods will run into the problems of singularities in the inversion problem, because you're actually carrying out an inversion. This Richardson, so-called Richardson-Lucy algorithm, the convolution algorithm based on Bayesian considerations, actually benefits from the positive definiteness of these distributions of particles in some properties, and is actually relatively stable. I wonder whether there are any questions right now.
It's not. I just want to see
how it works.
How it works, and especially model given the p probability. How?
All right. All right. Jiangyong, you wanted to ask?
Yeah, just just for clarification, is this the Deblurring the same thing as what the Heinrich people often use, the co-unfolding?
This is unfolding.
So it's the same thing, right? It's a busy
It is
unfolding.
the same thing, but this method, to the extent that I know, has never been applied neither in particle nor nuclear physics, to my knowledge. Of course, I may miss something, but it is unfolding.
Okay, so maybe in the end we can discuss this.
So let me go to an example, and this example will be, now maybe why this is connected to the 3D characteristics of heavy ion collisions. So when you model heavy ion collisions, then you observe significant anisotropies in momentum distributions of particles emerging from the collisions associated with the direction of the reaction plane. So, for example, this is a figure from that science paper that Yugang mentioned. So, nuclei collide with their centers displaced in the reaction plane, and then in the emission, there are significant anisotropies, collective flows developed with which are correlated with that reaction plane. So we have particles kicked to the side. Those that move forward and backward are kicked in the opposite direction. And around mid-rapidity, we have elliptic flow. So particles at this particular energy get higher, get faster in the direction perpendicular to the reaction plane than in the reaction plane. However, the problem that you have in analyzing the collision events is that you don't have a control over the reaction plane. So the reaction plane is shaking from event to event in the reference frame of the detectors. We estimate the reaction plane direction using the momenta, for example, relying on the fact that the particles get a kick in one direction, forward direction opposite to the other. We can take transverse momenta, weight them with positive weight if they move forward, with negative weight if they move backward, and construct a vector that will estimate the direction of the reaction plane. But the problem is that this vector is not ideally aligned with the reaction plane. So it will be, if you measure any characteristics of emission relative to this vector, you will deal with a situation where your estimated reaction plane is being shaken relative to the true reaction plane. So you're getting a blurred image. However, actually, when you construct a vector which is weighted sum of momenta, we actually know how this vector will be distributed relative to the reaction plane. So in the limit of large particle number, you expect this to be the central limit theorem to hold, and this vector will be distributed in a Gaussian fashion around some average with some widths. And actually, from the characteristics of the momenta themselves, you can estimate what the displacement is of this vector in the reaction plane and what the width is. That is, you can actually estimate what the blurring function will be. So actually, if you measure blurred results, you can try and deblur them. And right now, we deal with the blurring by using the Fourier coefficients. So we calculate the average values of cosine of 10 times azimuthal angle relative to the reaction plane. And we derive these coefficients Vn from from averages of different contractions. So for example, if you take momentum, transverse momentum at some rapidity, some magnitude of transverse momentum times this reference vector, you get this gets proportional to V1, and you can make other constructs that will be proportional to V2, V3, and so on. And you can get systematics of the Fourier coefficients of the azimuth of the distributions relative to the reaction plane. For example, here you have results from the Hades collaboration at 1.2 GeV from GSI, and they get coefficients are sync up to V8. The problem is with these coefficients that the low coefficients like V1, V2 have easy physics interpretation, but when you go to higher coefficients, it's unclear what their meaning is. And usually, if you start discussing these coefficients and their behavior with increasing n, people from outside of our community are usually baffled and don't know what we're talking about. So, what's our proposition? This is together with Mizuki, Nishimura, Kurata. Our proposition is to carry out as good determination of three-dimensional information relative to the reaction plane as one can, and refine the information with deblurring, getting the clean picture, such as cleaned up registration plate, and forget Vn. So to progress, let's first move on with a simple model which does not invoke azimuthal distributions, periodicity in the angle, and so on. Maybe before I progress, are there any new questions? Okay, so let me move on. So we consider a simple model, and this is a model which is one-dimensional, and it has all the issues that one normally considers in the reaction plane determination. but avoiding three-dimensional complexities. So we consider one dimension. We have a projectile, think cosmic ray. It's moving at unknown velocity, v. It de-excites, emitting 10 particles, and they are distributed with some distribution, dn, dv in the projectile center of mass. As a particularly difficult example, we take a box-like distribution. This task is the following. You measure particles in the laboratory, and you don't know what this unknown velocity is. It changes from an event to event. You're supposed to determine what the distribution of particle is relative to the center of mass of the projectile. Since you don't know the center of mass velocity, you estimate it. And when you study any single particle, you estimate it using nine remaining particles. And from these 9 remaining particles, you construct v prime, which is supposed velocity of the projectile, and you calculate the distribution of particles relative to this v prime. If you do that, so let's say this is our distribution. The red line shows you real distribution, box-like relative to the center of mass. If you carry out this procedure, you get the dashed line, so you get a distribution which begins to remind a box distribution, but it's actually smeared. And the smearing may be actually expressed in terms of a blurring relation. So the observed distribution dn dv prime is the real distribution dn dv convoluted with the uncertainty, with the distribution of the estimated projectile velocity relative to the true projectile velocity. You can estimate actually what the characteristics of this blurring function are just using central limit theorem. So here you actually have a real smearing, which is in the red. The estimate from central limit, which you carry out using measurement alone, is the blue line. And you can see they are largely on top of each other. If you carry out this Richardson-Luce deblurring, you get so using the central limit, not even bothering with the real one or simulated or just central limit, brutal central limit, you get the green line and it lies on top of the original. So you can find out what the distribution is relative to unknown center of mass. Any questions?
So maybe.
Yep.
Yellow. So this works, I guess, only when the Gaussian smearing, the width of the Gaussian is smaller, or should be smaller than actually the original distribution, because otherwise the assumption that the smearing is a Gaussian, if you vary that a little bit, you will not be able to recover, right?
Yes, this is the easy. So this one is an easy example, but in principle, you can basically what you deal with is that this depends on that. When you have the central limit working, this dependence is very easy. You can only use 2 lowest moments of the distributions, correlation, and you find the properties of the Gaussian. It's just a 2-parameter function. In this case, it's even 1 parameter because it's just width. So that's a very easy case. But what you can do is you can actually treat this problem seriously and actually do a simulation, knowing everything you expect about the system, and simulate what this Deblurring function can be. And in principle, you can simulate more complicated functions.
So the ability to do this in the end depends on your knowledge or the systematics on this dp dv prime, right? So
yes.
If you have some uncertainty, then you have an intrinsic limitation on what information you cannot recover.
Yes, but you can put this uncertainty into errors. You can do the restoration with errors.
Yeah.
So you can do it. You can do it. You can put uncertainty into. I will show example towards the end where this is actually done. When you go to real analysis of real data, you actually have to. You have to. You cannot go publish data saying something without errors, right? So you have to do it. And then you can argue, yeah.
So this blurring function is you can only do it by doing simulation, I guess. And
yes, although in this case, in this particular case, also in the problem of the reaction plane without detector inefficiencies, the formulas that from Voloshin Postkanzer work, which are used normally for Vn, assume just this kind of function. So when you determine Vn's normally, at least at the basic level, it's the same what's done here.
Yeah, it looks like this is routinely done even in most of the experimentals unfolding. They always assume some kind of Gaussian,
right?
Gaussian distribution,
right?
And then of course the resolution matters in this case, right?
Yes.
As Jiayong said, if the resolution is too big, and then you will have trouble to restore to the original distribution.
I will show you examples.
Okay.
The examples are scary.
Good.
Okay. So when we presented this first to wider experimental group, they said, okay, but we have, in particular, my collaborator is in a group where detector inefficiencies are really challenging. Basically what you can see is just within, largely confined to basically within a plane, what you see. Some with some wings, but it's basically, you don't have 360 in azimuth. You have too narrow, maybe 80-degree regions where you actually see stuff. So the problem was, so how do you cope with that? So I'll go next to next model. Model is this, again, one-dimensional. Again, we have a projectile unknown velocity that excites emitting n particles. But now the measurement is with the detector with strongly changing efficiency, E. And the efficiency is only 100% in the middle here of the viewing region, and then it drops to 0. It's sort of, and then the projectile passes in front of the detector. You don't know with what velocity, and the acceptance is, goes to 0 towards the wings, and basically it's sort of like viewing a decay through a keyhole. we increase the particle number because now the actually the particle number that gets accepted on the average is maybe 1/3 or less. So we started with the higher number. Here we have again this box distribution for original particles, and this in the red, and then this is the measured distribution, again with the same procedure. You, for every particle that you measure, you take those particles that you detected, you use them to estimate the projectile velocity, and you take your distribution relative to that velocity. So now you can see the the height has dropped by more than factor of 2. Then the tails are melted, and so yeah, that's what you see. Now you cannot now use the Gaussian because of those circumstances, but you assume that you know the fact that your defect detector is inefficient, and you just attempt, you don't know what this distribution is. You can adjust it, say, well, you start with this one which you measure, and you run it through the detector simulation. And you apply the Deblurring algorithm. And just to show you what now this blurring function has a non-trivial dependence on both arguments. So both the argument of the where the projectile was, where do you estimate the projectile to be, or where the particle was, and where you estimated the particle to be. And if projectile breaks up in the middle, so at v equals 0, you make an estimate. You find that the estimated projectile velocity is in the around the middle with some width. It's now more narrow than before because we have higher particle number. But if the projectile was somewhere here, so let's say at 1.3 to the rear, most particles which get accepted, they get accepted towards the center, and so you actually have a bias. Your estimated projectile velocity gets close to the middle as it's shifted. It has a width, but also a bias. If you assume that the projectile is at 1.5 over here, the bias grows, gets even larger, and the probability that you actually detect enough particles, we apply the cutoff. You need to have at least 10 particles for restoration attempt. This probability drops. So basically, this is the kind of blurring function or transfer matrix, which now depends on both arguments. But you apply the algorithm, and you get back your in the restoration, you get back your original distribution with the discontinuity. Any questions, comments?
For clarification, the bottom left panel, this red box, the red box is what?
This red box is an example of a distribution of original distribution when the projectile is at, these are arbitrary units, so it's at a half. So this one, so that's the distribution. If particles get emitted with this distribution, these particles over here get chopped off. Mm-hmm. These have a higher chance to be accepted in the measurement. And so you get a bunch of particles in the end, which are like lumped over here.
Yeah, thank you.
So, and then you make this assumption, it's that they represent true velocity of the projectile. You do all that and you get this distribution. So the distortion now is strong. This blurring function it looks like a narrow, but then this peak is shifting depending on, you know, where the projectile was. You know, if it's in the blind area of the detector, you assume your products come out with a bias, mostly in those parts where detector is good, and you lose the other part. Now let's go to a model for actual collisions, and now with the reaction plane. So we take a model which is, you know, we're working with the lower energy collisions. So it's a typical situation for 300 MeV per nucleon. You have light particles, nucleons, neutrons, tritons up to alpha. We take total charge of particles that get accepted into analysis is 50. We assume some rapidity distribution for sources. And then we assume sideward flow and some elliptic flow, typical values for this reaction range, and you know, some partition of energy between thermal energy and collective energy. Nothing particularly revolutionary, just you know, neither weak nor too strong. Oops. As an example, this is a normalized rapidity, which is often used in low energies, at low energies. So it's rapidity normalized to the beam. And these are the distribution of protons, distribution of deuterons. Deuterons are more narrow because they follow more the collective flow. These are V1 for protons, V1 for deuterons. We take the emitted particles. The reaction plane is distributed randomly in the azimuth, so we don't know where the reaction plane is. We estimate it with this Q vector method, so dividing particles into forward, backward, give them a weight, and get actually distribution of true reaction plane versus real reaction plane, which is fairly broad, as you can see here. One is from the simulation, the other is from central limit. Then we construct distribution of particles in azimuth for every rapidity and transverse momentum, and this is you know, this is the true distribution. Ends up being convoluted with the blurring function, which this is the blurring function. And now, since we have dealing here with the three-dimensional distribution in the momentum, we can look at different places, you know, at different rapidities in different azimuthal directions as a function of momentum. So as an example, we have here a distribution, a triple differential distribution. This is a rapidity which is half the beam forward direction in the reaction plane. So azimuthal angle is 0, but we look in the positive direction of the reaction plane and negative direction of the reaction plane. And you have here 3 distributions, original, measured, and then restored. So general feature is such that if you look into the positive direction of the reaction plane, this is the direction of the collective push. So yields are higher than if you go into the negative direction. And if you go to high momenta, actually the yields are different by 1 order of magnitude. If you just brutally measure, you know, estimate this 3D distributions relative to the measured reaction plane, you get these blue crosses versus red points, which are the true. And for one, you see already a lot of anisotropy, but not enough actually. Instead of you're off by a factor of several for higher momenta. If you apply Deblurring, you get basically restored distribution, which follows the original, and you're able to restore an order of magnitude of differences in the differences in the yields in the positive and negative direction of the reaction plane. The inset actually shows you the situation for fixed transverse momentum at the same rapidity. So this is this one. And what is shown is azimuthal distribution relative to the reaction plane. And the blue is with the uncertain reaction plane. So you get those blue points. If you correct for the blurring, you get the green points, and you follow the true distribution. So the beauty of this strategy is actually that when you resign yourself, well, I won't have a good reaction plane, you already get quite a bit of the insights, physics insights, and then the blurring just helps you to fix it. Now, why would you want to study three-dimensional distributions as compared to VN? Maybe any questions here?
Yeah, so sorry, I'm sorry to ask a lot of questions,
yeah, sure.
Daniel, but since you want some question, so I want to understand. So you're correcting for the event plane resolution.
Yep.
And why that changed the particle yield?
Because when you know the reaction plane, then anisotropies are sharper than when you don't know the reaction plane. If you start shaking the reaction plane relative to the true, if this were a flat curve, you would have no anisotropy left, right?
So I understand. So you have a PX. So if you have a PT, then it doesn't matter, right? This is just the reaction plane direction. The PX.
But what you have here, it's a 1 PT, and you move across all azimuths.
Right. I understand. But if you're only looking at the PT spectra, then the unfolding doesn't do anything.
Then the unfolding, yes, this unfolding here pertains to the azimuthal angle.
Right. So PX here basically is V1, right? You have V1, in fact, it tell you the event by event V1 distribution, right? It's kind of
no. PX is the true reaction plane. This is the true reaction plane component of the momentum.
Yeah. But that's the sort of the V1, right? I mean, it's
no. V1 is the first moment of this distribution here.
Okay.
So V1 would be, I could take this distribution, this green one, and calculate V1. I could calculate V2, V3, and so on. I could go calculate all V's. What you have here is a combination of all these. It's just what you would see with your eyes if you could fix the reaction plane. You don't transcribe anisotropies onto the moments. You just look what you have as the anisotropy. Why would that be useful? So let me show you results from simulations, from transport simulation. So as an example, here we have transport simulation of the particular system that there's the collaboration that my collaborators from works on. And this is a three-dimensional, three differential spectrum calculated in transport. Basically, it's the same situation what you've seen here. Okay, this one is, I think this was for deuterons. Yeah, that's deuteron here. What you see here is for neutrons and protons, such a distribution. And it's actually, again, component in the reaction plane, phi is equal to 0, rapidity is half of the beam rapidity. Now, what you see here as distribution, it doesn't look like the other one in the previous figure. Here, since one assumed thermal model convoluted with the collective flow, you get basically a parabolic shape in the logarithmic scale, right? It looks Gaussian. But when you calculate in transport with a fixed reaction plane, you don't get a Gaussian. Actually, it's interestingly, nobody looked at that before because this was something you couldn't measure, so why bother? And you can see, these are piecewise straight lines. There's a cusp that's in the direction of the collective boost. Usually when you see cusp, you can say, well, it's presumably Coulomb, but Coulomb is there for expected for protons, but why for neutrons? Then you see here piecewise straight lines, and you see different slopes on the different temperatures, you would say, on the this is spectator side, and this is participant side. So on the participant side, you see a hotter system. Then on the spectator side, there's a difference in the slopes here. Then you have a knee on both sides, and then you go past to another, higher temperatures, again, different from the two sides. So actually, it's a different picture than normally we use, also at low energies, of convoluted collective flow with thermal motion. If you average this over azimuth, you would lose the cusp, you would lose the knee. These slopes will become the same. You would not restore all of this out of VNs. Another example, simply different distribution, again, from transport. So, when the nuclei collide, you have this hot, dense matter in the middle. And, you normally go after want to study properties of that matter, and preferentially looking with their detector straight from this side, not having to go through spectator, cold spectator matter. This, if you go with VNs, you compare emissions through, directly to vacuum and going through cold matter. But if you do three-dimensional analysis, you can actually position your detector and just look. This is in the direction perpendicular to the reaction plane. And people right now are interested in so-called symmetry energy at supranormal densities. That is the response to neutron-proton imbalance, energetic response to neutron-proton imbalance. And depending what you assume about the symmetry energy, how quickly it changes with density, you get different ratios of neutron to proton yields when you look from that 90-degree direction towards hot matter. And if symmetry energy is stiffer, pushes out particles, neutrons at high densities, then you get a higher ratio of neutrons to protons at higher momenta. interestingly, you get compensating behavior at low momentum. Any questions? So my argument is that when you use this triple differential distributions, you have access to new insights into physics that you didn't have before. Now I'll go to another example, which is completely, which is sort of more not the method, but detector related. So this is at FRIB. There's a so-called MONA group that measures neutrons, and they have been studying decays of shortly lived isotopes. When these isotopes decay, you measure the products, and out of those products, you try to figure out what the spectrum is of the decaying nucleus that was short-lived. As an example, this is so basically you just construct invariant mass of the products. You take you subtract the minimum mass, and that's your decay energy, and you look for bumps in the spectrum. So in the measurements of decay of oxygen-26, they found this kind of spectrum. And you can hardly say whether there are any bumps in here. Just lukewarm spectrum. Now you can analyze the detector performance that's used in here. So measurements of 2 neutrons is hard. You have low efficiency. Their resolution in energy is poor. So that usually whatever you measure in that kind of fashion is sort of structureless. That's this spectrum. We apply the blurring. One of the author of the thesis where this originally was measured has constructed the blurring function or transfer matrix. We applied the blurring now with errors, where we sample the errors of the measurements. The errors in the blurring function are actually relatively low compared to this Poissonian errors from low statistics. And after the blurring, you begin to see bumps. And these bumps are indicative of energy levels in oxygen-26. So one at 0 MeV, there's one around 1.3 MeV, then there's another one around 5. And so you begin to see structures. In parallel, analysis was done using a deep neural network. These are the peaks from DNN that have been identified. But in the blurring, we do not assume any peaks. We just decompose that spectrum. And maybe let me show you the blurring matrix. So this is the blurring matrix actually for this situation. There's a true decay energy, measured decay energy, and these are the type of distributions. Usually you lose energy and events are lumped sort of in low energy region. And that's this blurring function. All right. So I'm getting to the end. So the blurring has a strong record in optics and fields that rely on optics. So forensic science, astronomy, and microscopy. The blurring the benefit of the deblurring is that you can see better maybe some features of the data which you might not see without the deblurring. Usually when data are blurred, are distorted, you resort to comparisons with theory, and you filter the theory through the detector performance. But when you do that, you may miss some features of the data. There's no reason to confine the blurring just to photons. In these cases, actually, with the reaction plane, the blurring function depended on the distribution itself. It was possible to carry out restoration. Effectively, it should allow control of the reaction plane in energetic heavy ion collisions. Another area where we have arrived at significant progress is in the analysis of correlations to get sources out of correlations. Correlations are, it's the domain of more of a Fourier transform, yet the blurring works there as inversion too. I should thank my collaborators. So Mizuki on the reaction plane problem. Pierre has been working on the blurring with this MONA collaboration, and in particular Paul Guy, Thomas Redpath, and Thomas Baumann, Pablo Giuliani helped us with neural networks. Thank you.
Thank you very much for your excellent talk. So in this talk, Paul introduces their new proposed method for Deblurring, and then give us some application case for the exotic decay and the other reactions. So now the issue is open for questions and comments. So Jia Yong, please.
Pawel, thanks for the talk and explanation. So I maybe just some comments. Can you, if you go back to one of the V1, like the PX plot as an example, I think this method has been used quite often in the high energy heavy ion collisions, but of course the signature you're looking is different. In other words, we also have this transfer matrix that accounts for experimental effect, and we have a measured distribution, and we deblurred it. We call unfolding, and we get the original distribution. The example I'm pointing to is that we, for example, I think Phoenix did it probably like almost 10 years ago, where, at high energy, V2 is the only dominating component, right? So basically, we have a similar distribution like what you show on the top panel, where you have the true V2 plane, true reaction plane, symmetric reaction plane, and also the smeared one. You have this dispersion plot in the top, which you use to unfold the angle dependent distribution. But of course, there, once you unfold it, you are dominated by V2 and the V4. You can only measure V2, V4, V6, right? So it just turned out V4, V6 are very small. So in the end, this doesn't buy you much, because it's not like a low energy where V1, V2, probably they're both important, and therefore you get the entire probability distribution is better. Yeah, so this is just a comment. I think we use this, I give you one example, but we also use it, for example, people, I think, for example, people measure the event by event. Here is event average distribution, right? This is the event average distribution. We actually try at the LHC, the all 3 experiment, try to measure the V2 event by event probability distribution. So in other words, you measure the V2 in each event, you construct a probability distribution, see how the flow fluctuates event to event. And there we also have this, of course, the transfer matrix, which allow you to do this kind of thing. I think just the way how you, the application is different, but I think the method has been used widely. That's my comment.
I have not seen application of Richardson-Luce in the nuclear or particle context.
Yeah. So this Bayesian unfolding is implemented in the root. It's called root unfold. There's a package that is quite common. Yeah, it's root unfold called in the root. Basically,
okay.
I think most of the people in high energy and at LHC and and also I think they use that tool.
Okay.
I can send you some reference.
Okay. Yeah. Well, okay. I would be grateful.
Okay, Ziwei. Yeah, Ziwei.
Yeah. Hi, Pawel. Thank you very much for the talk. Yeah, great talk. So I have two questions actually. One is that it seems like if you know the blurring function exactly like this curve, Gaussian curve, then it doesn't matter whether the curve is wide or narrow. I mean, it can be as wide as it can be. I think you will get the good answer out of it, right? If you know the shape
I don't,
without error.
Yes, but I suppose there should be a limit, because I mean we intentionally chose here singular behavior. What happens is if you have singular behavior, the convergence becomes slow. But so far we didn't find a hard limit. And of course, yes. And if you have white function, this blurring function, and it has some significant error, and presumably at some point this restoration will result in
once you
noise
consider error, then it's a totally different story, right?
Yeah.
Then
So just like
everything.
here, you have significant error, but you still can see bumps through the error.
Yeah. So and my second question is, how is this related to the lattice QCD problem? They have this inversion problem as well to get from the lattice data to get the spectral function or something like that. The blurring function exactly, right? It's like but it's virtual.
So what I've seen, because my interest in inversion has a long, is extended over time. So I've been using other inversion methods, and in particular maximum entropy method. And I saw maximum entropy method used for lattice. This is a different method. I think it has, it does not have, to my knowledge, there is no mathematical proof that, it should, or mathematical understanding of its extent, where it should work or where it shouldn't work. There's a lot of practical experience with that method, and it's easy to employ and widely applied in the optical situations. I don't know about its use in lattice.
Yeah, like in your opinion, which
I would go with this. This one works.
Will have the lattice, or the lattice method will help here.
So far, in every case, we've been working on 3 cases where I had experience with other methods. This one was always superior. This Bayesian method.
Okay.
I cannot guarantee it in every case, but the point is, it's one of the first contenders. One should try.
Okay. Thanks.
Yes. Yeah, Paul. So, yeah. Concerning this screen, this slide. So, when you use Deblurring these techniques, so you first should know the, like the energy level, and then you can, constrain such kind of Deblurring technique. But if you don't know this energy level, before that,
so normally normally the strategy. So if you had, had ideal measurement, you would measure this decay spectrum and look for resonances, and each a peak would be interpreted as a resonance in this decaying system, oxygen 26. Because of the detector performance, this spectrum is so smeared that you don't see structures.
Right.
Once you apply the blurring without prejudice that there are any peaks, you begin to see peaks. And then you can say, oh, this is, of course you may turn at this point to theory and ask, is there a level expected here? And in fact, there had been calculations which have shown peaks in these regions.
Okay, I see.
If you go too high in energy, the levels begin to be so broad that you'll likely not see them. You will not be able to tell it from continuum.
Yes. For the high decay energy, you mean the peak will be very broad, and it's difficult to see such structure.
Right.
Okay. Good. Okay. Any questions? Comments?
Guo Liang.
Oh, Guo Liang.
Hello, Professor. I have a question. Okay. So because my students, she is working on the jet reconstruction, and during her work, she used like unfolding to reconstruct the jet mice and jet GT. So in this case, she has two unknown variables, PT and mice, and we have both. We have two resolutions, and so I'm wondering, is it possible to extend your Deblurring method to more? The many variables. In your case, you always it's one variable. Yes.
Yes. So yes, this was these were easy cases of one dimensional, but even so, even here you have a choice, because you could take momenta of all three particles, and you could work on momenta. It's actually your decision, sort of what level of complexity you need. And in some cases, lower resolution may work. Already at the lower resolution, you may get good restoration, or maybe you need to go to more variables. It's a decision, and how much information this extra variables bring. In optics, normally restoration is actually two-dimensional, because you have a matrix of pixels, which is 2D. In biology, it's 3D, because you have pixels, but then you go over layers, you focus the microscope at different depths. So it's 3D. In correlations that I mentioned, we work on 3D because we go after deformed sources. So actually the matrix is 3D times 3D. And so you can go to more dimensions. It's just the matrix. You still work with matrices, but the indices on one side of the matrix and indices on the other side of the matrix may go over a larger number of dimensions.
Okay, so regardless how the variables are correlated, so it will be always work.
Can you repeat?
So, I mean, so between the variables, the variable can be correlated, you know?
Yes.
Yes.
Yes,
so
it can be
your
correlated.
method take care, can take care of this kind of the correlation between many variables?
I think the choice of variables is a choice how you describe your the characteristics of the system. And you can, whether they are, you know, there's some redundance that they are correlated or not. I don't think it matters because it's just, it's your choice how you describe the system, and you should be free to describe in the manner in which you want. So for example, in this models or exercises that we went through, we could work with one-bodied information, but we could work with n-body information. Both are legitimate. We found that if we work with one-body information, it's sufficient for restoration of one-body properties. We didn't need to expand the space, but you can expand. I don't think there is a limitation in the how complicated you make or redundant you make the description.
Yeah,
I
so,
see.
so if I
Okay.
if I can just add something here, I mean, the unfolding based on the Bayesian theorem, you don't care how many dimensions. All you need is the relationship between the input and output, right?
Yep.
The regularization is done naturally by the iterative procedure. So if you try to use some other unfolding mechanism like unfolding like SVD, you know, singular value decomposition or other method, then when you have a multi-dimensional problem, this regularization need to be chosen very carefully because you know you need to impose a correlation between beings, and if you don't line up the elements correctly, you will get a wrong result. But for Bayesian, it really naturally doesn't matter the dimension. You can just linearize, you know, multi-dimension into a single histograms.
Yep.
Yeah. Just add to that. Yeah.
Thank you. Thank you for your explanation. Thank you.
Yes. Yeah, I think such kind of technique can be applied to many reaction phenomenon. So as you mentioned, like correlation. So when measurement is for like a proton-proton correlation function,
right?
Momentum correlation. Yeah. So usually, if we did not take into account like experimental field, and then the momentum correlation function strength will be lower than the true one. So I think if you use this Deblurring technique, then the proton-proton correlation function will be correct for the true strength, and then can get the real source size, such kind of information.
Right. I mean, the only thing which you know, the practical limitation, but also the you know, it's a lever arm on which this method relies, is that you relate positive definite quantity to positive definite quantity. So the measurement is of positive definite quantity, and what you look for is positive definite. So source function is positive definite, correlation is positive definite. What's interesting, what appears is in a situation where you have not positive definite quantity, you can add a constant, you know, like, but it's bounded, then you can add a constant and make it positive definite quantity and still work with that method.
Yeah.